occasionally organizes. Great honor to be here in honor of Claude Itzykson. I searched my memory, but I couldn't locate where I might have met the man himself. But I can say that he has been a presence in my life for at least since 1985. Well, how so, you may wonder. Well, what was happening in 1985? I was a diploma student at Imperial College in London, about to embark on my PhD. And no doubt one of my enlightened lecturers had recommended the book by the great man. Here's this yellow tome. And I must have been very strongly motivated. I can't remember who recommended to get it. So I did go out to Foyles, the big bookstore in London at the time. And not only that, I spent an amazing £48.95 for this book. And this was in the days when the pound still was worth a lot of money. So it significantly ruined my finances at the time. I was just a simple student. So what else was happening in 1985, maybe more to the point of the meeting we are currently holding here? Well, at roughly that time, and I should thank the previous speaker for giving a brilliant introduction of things from the 80s that happened in the 80s. Very fruitful ideas concerning two-dimensional random geometry emerged and found many applications. And of course, one of the prime initial motivations was to describe dynamics of two-dimensional world sheets of bosonic strings. But of course, many, many things came after that. So today's story, what I'm going to talk about, will be really a further development about these ideas of random geometry, but with a twist. And the twist will refer to causal structure. And what I'll be talking about is a candidate theory that comes out of this, of quantum gravity in 4 dimensions in terms of causal dynamical triangulations, or CDT for short. So to put things a little bit in context for you, so what is the overall outlook, also maybe in contrast to motivation, what motivated some other talks we've heard at this meeting. So we are finding many new results by looking now at a single concrete specific model of quantum gravity. And it will be very simple, and there will be very few parameters in this game, 3 parameters, so screws I can turn, and I will consider that as a set of this model. And there should also be a health warning. My primary motivation is really physics. So I don't mean this, I don't want to put any value on one or the other, but it means that I have specific, ultimately, hopefully, experimentally or observationally verifiable phenomena in mind that I want to describe. And it's not that I had a great array of analytic tools at hand to do that, but nevertheless, that's my motivation. So I'll try to push it as far as it goes, and I'll illustrate to you by what kind of methods one can get to what kind of results. So it's a very explicit framework, one obtains concrete and quantitative results, and that might actually have the benefit, very rare these days in theoretical high energy physics, that I might get something out that's wrong, falsifiable, the sort of thing is. So if you want to read more about this, there is a physics report by myself and collaborators, but this is already a few years old. So some of the results I'll talk about today are actually, you won't find in there. Okay, now which insights, which in part are empirical in the sense, they are the result of trial and error of what we've done, are behind the success of this approach so far. So I would say a couple of insights will actually come, building on what's done by other people starting precisely in the 80s and involving quite a few people here in the audience. So the first one is as follows. So for the purposes, at least, of the quantum theory and the non-perturbative quantum theory in particular, assembling curved spaces, curved space-time, piecewise flat objects from identical triangular building blocks seems to explore the space of all geometries very effectively. So that space appears as a carrier space of when you do quantum theory, when you do path integral, when you do partition functions. So that's what happens in everything that's called dynamical triangulations, but also that underlies quite a few other methods that people have already talked about, mainly in 2 dimensions at this meeting. So here that's, someone else's dream of a sphere, that you might recognize the similarity to the previous picture, so that's actually a typical path integral history, glued from triangles. In this case, this is Euclidean 2-dimensional quantum gravity, triangulated, and these are all equilateral triangles, but of course it's not an isometric way of embedding them in 3D here in this picture. Now, dynamical triangulations, or my particular incarnation, causal dynamic triangulations, is also very close in spirit, as I would argue, to the classical theory of Einstein. So it's kind of the rods and clock picture. So we explore our own universe, the non-trivial curvature properties of our own universe, by making measurements. So rods and clocks, so we make time-like, space-like distance measurements. And you could say that the metric, this is only kind of a refined concept that of course captures this extremely well in the realm of smooth manifolds, but really it's a derived object. So we'll use a similar idea, and actually using these equilateral triangles or higher dimensional analogs thereof in quantum gravity really implements a very similar idea. You have a kind of a yardstick and you just explore distances, and that's a more fundamental concept than the metric, and it gets you quite far, and it's very useful in the quantum theory, as you'll see. Now, the last insight is, I would claim, really due to colleagues and myself who worked in this causal approach of things. So it's, I would say, it's simple. This method is as simple as it can be, but it's not simpler. And in particular, what we found, again, by experiment, empirically, is that random geometry, at least when you try to do quantum gravity in higher dimensions, must be replaced by causal random geometry. So there's an extra structure which apparently you just have to put in by hand in order, for example, to get something that looks like a good classical limit out. So that's really the transition from dt to CDT. Okay, so what's my playground? What is the object I try to understand? Well, this is the magic formula in quantum gravity. So that's the sum over all histories. And this is, of course, plainly speaking, the gravitational path integral. So I'm not coupling matter, so it's just pure gravity, if you like. So what one is instructed to do here is, in this very formal right-hand side, is to integrate over all curved space-time, so little g they're called, and each of them is to be weighed with a complex weight factor e to the is, where s is the Einstein-Hilbert action of the curved 4-dimensional manifold. So you're supposed to do this integral with respect to some, to be specified measure. So that's extremely formal. This is an object I call z, anticipating I'll be thinking of that as a partition function in a minute, and it depends at least on Newton's constant and the cosmological constant. So to make sense of that, that's in a way the crux of the business. So what I do, very much in the spirit of lattice quantum field theory, is also already mentioned earlier today, but here it's for gravity, and it's based on dynamical triangular lattices. So you might ask, in the old days one could say, well, how do you put Yang-Mills theory on the lattice? Now we ask, how can you put gravity on the lattice? That's actually the wrong way to ask, because, space-time, you put fields on space-time, but gravity is space-time. So analogous to that idea, we are saying, well, the lattice is space-time, so we have to make the lattice itself dynamical, and that's the natural and right thing to do, or so it appears with hindsight. So what I do is I substitute this formal expression by a sum over objects that I can handle in an easier way. They are regularizing the smooth curved spacetimes, and they will be given by triangulations here. So what I make sense of this object by writing it as a sum over inequivalent ways of triangulating manifolds by 4-dimensional analogs of triangles, so there are 4 simplices, and for each ensemble of gluing these objects together, say it has n building blocks, I evaluate an analog of the Einstein-Hilbert action. This is also called the Regge, due to Regge. So T is the argument, stands for triangulation, and this is a simple weight factor, which most of the time is anyway 1, depends on the order of the automorphism group of T. So what I do then, I mean, my building blocks have a certain, they come with a length unit, so lattice cutoff, UV cutoff, if you like. So what I then want to do, I want to understand how this object scales as I take the regulators away, and whether I can recover an interesting interacting theory of gravity in higher dimensions like that. So here's a list of some recent contributors. Some of them are in this room, so there are more, I'm sure, which have contributed to this game in dimension, 2, 3, 4. But as I said, my emphasis today will be on dimension 4. So on this slide, I reveal to you, what I have to use and to assume in order to get started, in order to set this formalism to work. So I'm using a minimal set of ingredients and priors. Well, small, but not too small. First of all, we rely on several. When it comes to quantum gravity, people are sometimes prone to throw things overboard. Things like, locality, unitarity, quantum gravity, the Planck scale, anything goes. Well, the problem with that is that to actually construct realistic models that implement these ideas in some way and get some interesting physics, some numbers out, that's really difficult. So don't lightly abandon love principles, and one of them is certainly, which I'm using, is path integral, or just the quantum superposition principle, locality, and I'm putting into my path integral in a way which I'll explain in a minute, a causal structure, so it's not Euclidean quantum gravity I'm doing. There is a notion of proper time that to some extent, of course, is related to the fact of having a causal structure, but this can be relaxed. I'll say something more about it later. So what you see here is a piece of a causal triangulation, and in 2 + 1 dimensions. So this already gives you a flavor that things will be arranged kind of in slices, stacked, so the time direction goes vertically up, and one is interpolating between spatial geometries of fixed time by putting in these triangulated building blocks. In order, but it's very crucial for us to evaluate the path integral, is that there happens to be, on the class of geometries you're putting into the path integral, a weak rotation, so an analytic continuation, the result of which is a subset of Euclidean triangulations. And over these we then try to perform the sum. Otherwise, so these are basically the ingredients, so it's really standard tools of quantum field theory, and of course critical system theory, the way we then treat this after Wick rotating. And so there's no matrix, there are no special symmetries, there are no extra dimensions, it's pretty bare bones. And in particular, our configuration space is a very straightforward regularization of the curvature degrees of freedom you have in the classical theory. And they're encoded now in the way these triangular building blocks are glued together, and you pick up deficit angles and local curvature. There are very few, as I said, few free parameters, so there is the lambda cosmological constant in Newton, and what turns out to be important in 4 dimensions is an asymmetry parameter that at the level of the bare action is simply a parameter that relates time-like distances, a finite scale that relates time-like distances to space-like distances, but it assumes in the non-perturbative regime, where we find an interesting result, it becomes like a coupling, an important coupling. What we do relies on the idea to start with a regularized setting, look for non-trivial scaling limits, following standard logic, going to a second-order phase transition in the phase diagram, we find. And there is a considerable degree of universality, and of course that's something you hope for. So you hope for that some of your arbitrary starting point or regularization details will be forgotten, and you also hope for the fact that if there's a quantum theory of gravity, it's unique, and there's not an infinite parameter space of these objects around, because otherwise, I mean, how are we ever to pin it down otherwise? Crucial for this game is to be able to extract quantitative results, in this case, mostly using Monte Carlo simulations. So that's how we know about the system. That's how we explore it, and how we try to get a further analytic handle by using input from what we see in the simulation. So it should be a give and take, and you'll see some explicit examples of that. So let me jump straight in. So a classic result, which is already, okay, I'm not giving the reference here, this is already more than 10 years old, is that we can, by just taking a big superposition of highly curved gluings of triangular building blocks, just weight with this Einstein action, if we pick out a specific variable, I told you I have a natural notion of time, I have a kind of slice structure, if we plot for each time the spatial volume of the universe, so topologically we make it compact, for simplicity it's a 3-sphere at any given moment of time. If you look at that, the volume of that 3-sphere, we're just counting the number of building blocks, yeah? And we plot that against our time, our proper time, and we do that in the sense of expectation values, so we let the Monte Carlo system run, of course, and we pick out a triangulation, and we always measure the so-called volume profile. Then the expectation value of that gives this very nice curve, and you can fit it beautifully. So this is time, so it's proper time is in steps, and this is a 3-dimensional volume at a fixed time of our universe. It can be fitted with great accuracy to a mini supersurface calculation of a de Sitter space. And here this is this footnote. Well, actually, if you believe maybe Hochauer-Lifshitz gravity is relevant, we cannot exclude fitting this to Hochauer-Lifshitz gravity. It might also be an indication of that. We have too few observables to distinguish between the two. But certainly what we've been advocating is that this is compatible with 4-dimensional general relativity. And it's quite remarkable, because what we are comparing this to is, because we ubiquitated, to a Euclidean solution of the Einstein equation, which are derived by assuming a priori isotropy and homogeneity and the presence of a cosmological constant. So when we do that classically, of course, we throw all the local degrees of freedom out, and we reduce just the system essentially to the volume or the scale factor. So the scale factor is this AFT. So that's the answer, that's the cosmological answer in a proper time notation in the continuum. So if you make this cosmological, vastly simplifying ansatz, a solution you find has this characteristic cosine squared behavior of the scale factor. And the scale factor just gives you the linear scale of the universe, so that's little a. So what we are seeing in our plots was a cosine cubed. Yeah? So it's just essentially reproduces this behavior here. So, of course, we haven't put in any assumptions about homogeneity or isotropy. It just, we see it. So, it's a large-scale property of our so-called quantum universe that it has this anisotropy and it has this shape function. And this extends beyond just looking at the classical shape. So, if you look at the quantum fluctuations around that shape, you can match it beautifully to a mini superspace approximation you can make, where you then, in a second order truncation, you can also compute, you have an effective Hamiltonian that governs the fluctuation. You can easily compute, well, not compute exactly, but you can easily find its eigenmodes, and they also match beautifully without any further fitting what we can extract from our computer data when we zoom in on a specific observable, the volume at a given time. Well, there's a lot of talk about emergence these days, and you have the idea, you get the impression nowadays you don't derive a result, everything emerges, So what I would claim here, this is really a prime example of genuine emergence. I just put in highly quantum fluctuating geometries, And what you saw, I mean, the picture of the sphere, you know, that just characterizes, gives you a feeling for how far the individual configurations, typical configurations in the path interval, are away from any nice-looking classical geometry. And also, you shouldn't be misled by a picture like this, because when the only thing we are zooming in, it's, you know, now this is a Monte Carlo snapshot, so I haven't averaged like I did to get the figure, the plot on the last slide. So this is what I call a snapshot of the universe's free volume. Note, it's not the universe, because it only really plots the three volumes of the universe and makes it into rotational body. So if you look at the local geometry of this de Sitter, what looks like a de Sitter space macroscopically, it will be totally wild. It will not look anything like approximately, you know, flat or approximately constantly curved. So don't be misled by this picture. We don't depict these quantum fluctuations, and they are very, very considerable for the small universes we are simulating. So nevertheless, it is very remarkable that from this, you know, realization of quantum fold, you could say, you retrieve at least some properties that you can match in a very nice way to outcomes of classical GR. And let me stress, the way this comes about is not because we are suppressing quantum fluctuations on small scales, but we are in a genuine non-perturbative regime, so very far away from the regime where simply the classical action dominates. So we have strong contributions from, you know, the entropy or the matter, whatever you want to call it, that bring about, so they contribute in about equal measure to bring about this nice de Sitter shape you saw on the previous slide. Now, the question is, how is it possible that we can observe nice semi-classical behavior when everyone else finds only branch polymers? So, what was the story about branch polymers? Let me remind you about the phase diagram of the precursor of the causal dynamical triangulation. So, these were dynamical triangulations, Euclidean, so a way of doing Euclidean quantum gravity. Yeah. So, this was beyond, in 3 dimensions and higher. This was a typical phase diagram. So, you have 2 couplings. Kappa naught is 1 over the Newton constant, and lambda is a cosmological constant. What always happens in this model, also the CDT, is that you have to, the first step is to fine-tune to the critical surface, so where lambda becomes critical, and that puts you in, that gives you an infinite volume limit, that allows you to take n equal to infinity. Now, so this is the one would be the phase space, and unfortunately, the typical geometries you find, or in other words, if you look at things like very rough characterizations of the geometry, like the Hausdorff dimension, these objects are very, very far from an extended 4-dimensional geometry. So that's something you would like to find. So that's something we found in CDT, but that was never seen, no way, how one looked at it, when doing the same thing in terms of these not causal, so just isotropic Euclidean triangulation. So you find for large kappa naught, you find this typical branch polymer phase, where even if you take star arms 4-dimensional building blocks, it's an entropic effect. They preferably like to arrange themselves in these filaments, these branching filaments. And therefore, on no scale does this really look like a nice extended 4-dimensional space. And for small kappa naught, you get conversely a very degenerate phase, which is a crumpled phase where you just have basically a couple of very singular vertices, where around which all the simplices crowd, no matter how many you have of them, and that was called the crumpled phase, and it basically corresponds to an infinite Hausdorff dimension. So that's also not useful. So what does make all the difference? Well, it appears to be the causal structure. So what do I mean by the causal structure? How does it find entry in this formalism of working with triangles? Well, I give the elementary building blocks I use a Lorentzian, that is a Lycon structure. And the gluing rules that I have ensure that I have kind of a well-behaved, so that's something I'm imposing, a well-behaved causal structure overall. So this is something, well, it's motivated by certain classical ideas, but this is something I didn't know I should do, impose as restrictions on my past integral histories. So it's an empirical fact that if I do this, I get very nice results. Whereas before, in the previous incarnation, when I didn't have the structure at all, it was different. So, and I never see extended geometry. So I just wanted, for the remaining part of the audience, just very briefly recap what is causal, what do we mean by causal structure, just to recap. So let's say we have in 3 dimensions, this is time, x, y, z. If I sit at any point x, I have a local icon structure. So that's an extra structure that's simply not there in a remaining manifold. And this is not, well, this could be a piece of Minkowski space, but it's completely general. So I have a local icon structure, and the point here has a past, so everything in the past icon, inside the past icon, and stuff in the future. So it's an extra structure that a Euclidean space doesn't have. And what happens in particular is that, well, one should say, once one has such a causal structure, one can then talk about causality. So that's something different. That is, with respect to that causal structure, are certain phenomena causal or acausal? For example, propagation of particles. So I just want to emphasize there's a difference between causal structure and causality, because some people say, well, you're working with a picture that imposes causality. No, that's not the case. We want to have a causal structure there. And only when I have that causal structure, I can talk about things being causal or acausal. How could things be not very causal? Well, imagine you are a one-dimensional closed string, right? Let this be time. And, well, then you get these nice trouser pictures that people draw. Yeah? So one string splitting up in 2. So here, say, it's embedded in some Minkowski space. What is a remarkable thing about this? Well, there must be a singular point in here somewhere where the Lorentzian structure goes singular. So Lorentzian structure, that is, say, if you think of this thing inheriting a metric from the ambient Minkowski space, just a 2-dimensional Lorentzian structure with plus-minus metric. Yeah. So what is wrong with this point? Well, at some stage you see there are light cones everywhere here. Yeah. But there's a point here where the light cone doesn't quite know where it's supposed to go, left or right. Yeah. And that's a singular point, so the Lorentzian metric is singular there. And it's intrinsic, it doesn't depend on the embedding. Yeah. So this is something, well, it's a causality violating point. Yeah. So that's a string picture. And if I extend this to higher dimensional geometry, yeah, then I would say, well, this is a universe, but let it not be 1-dimensional, let it be 3-dimensional, let it be a 3-dimensional sphere. I could also have such phenomena, right, where I get multiverses, yeah? Space splits up into several components, but it would always be accompanied by singularities of the Lorentzian structure. So that's just something I want to emphasize. And, well, depending, classically this is totally forbidden. In the quantum theory, well, who knows? But of course, even if you do quantum field theory on an object like that, you get very unphysical features like infinite particle production. So this is, well, it has a potential for things to go wrong if this really has a Lorentzian signature. So what you have to do in your theory, you have to tell me how you deal with these things. So the way we are using this is we are forbidding our path integral histories to have such acausal points. There is no strong physical motivation for this because a path integral history is not a physical thing, it's not observable. So it might just be that we have to include all these guys in the path integral to get the right result. But we've tried it and it didn't work. So we suppress things and we suppress things like this. So this is again time. So we don't allow the universe to split up into several pieces, and we don't allow it to have handles. So in particular, so these things are just ruled out and trouser points don't appear. So that's just a choice on the configuration space of the path integral, and then you just see what you get. Okay, as I already said, we derive nice results. So it seems to pinpoint the difference between doing things the causal way with a causal structure and doing them without that. Now, there is a slight subtlety in the sense that we have in CDT this sliced structure I have already mentioned to you. So here's another picture of that. So this is proper cap T, then there's a purely spatial triangulation, and this is step T plus 1, and in between sit our space-time building blocks. Yeah? So you interpolate between adjacent slices. And by just saying, look, this spatial slice always has to have one and the same topology. Of course, I'm suppressing topology change, I'm suppressing baby universes. But it seems to be very much tied to the fact of having a time there. Yeah? So maybe what is the crucial, ingredient of CDT that produces nice results? Is it the presence of the time, or is it the presence of a local causal structure with light cones? So in order to answer this question, we've introduced a new version of CDT, quantum gravity, a few years ago. It is called locally causal dynamical triangulations. You could call it LCDT for short, where the causal structure and the preferred time are dissociated. In fact, there is no preferred time in this way. And we have repeated in 2 plus 1 dimension, we have repeated the standard analysis, numerical analysis of phase structure, of getting out these volume profiles, and we find that key results of CDT appear unaltered. So a preliminary, well, this is good evidence, certainly in 3 dimensions, that these two things are, well, ultimately lie in the same universality class, something like this. So, and also that it's a causal structure that's responsible. So an implementation of kind of local light cones like that, and not so much the time slicing. Although one should say, to have the time foliation is extremely convenient, also in solving the model, but it doesn't seem to be strictly necessary. So this is some extensive work, some Jordan, one of my PhD students did. So just for the people who like to do things in 2 dimensions, just to illustrate what the essential difference is between CDT and LCDT in 1 plus 1. So this is the usual CDT building block. It has a space-like edge, 2 time-like edges, and you're instructed just to glue these objects together to get a piece of Lorentzian space-time with curvature, deficit angle. So this is what it looks like. It has a slice structure. And you can't do anything else but these slices with these building blocks. And in higher dimensions, it's just the same. We have a few more building blocks. Now, by contrast, what do we do in LCDT? Well, you need at least one other building block to break up the slicing structure. And this is the additional building block in addition to this one we're using. And you see it has 2 space-like edges and 1 time-like edge. So this is a light cone. If I wanted to draw one, I mean, it's flat by definition on the inside, so I know where the light goes. Having this and this building block present allows me to make pieces of perfectly causally well-behaved, in the sense of local light cone structure, space-time in 1 plus 1 dimension in this case, but no visible and no preferred time slicing that coincides with a lattice substructure as it did here. So what I do have to implement in order to preserve locality is just a local light cone condition. So I have to make sure that I have just exactly in each point 1 forward and 1 back light cone. And it puts some restrictions on what I can do at the vertices. So but this is a perfectly well-behaved Peter space-time that does it, that implements it. So to recap, so this would be DT, purely spatial building blocks, Euclidean gravity. That's what one does. Usually, that's Liouville gravity you can do with these things. CDT has these Lorentzian type building blocks, and LCDT has this generalization with the extra building block. My former master student Ben Royal and myself, we have looked at, tried to understand, well, is this in the same universality class as CDT? That's what one would conjecture on the basis of the 2 plus 1 dimension result, or is it actually, well, could it be DT? Because we generalize things to that extent. Well, it's still causal, but it's a looser structure, so you get more types of objects. And for that, we've looked at the Hausdorff and the spectral dimension, and well, putting a question mark here. So we have some numerical evidence that CDT and LCDT are in the same universality class, but the data are quite bad. For the spectral dimension, well, that's 2, that looks pretty good, but that doesn't distinguish it from dt. So CDT and DDT both have spectral dimension 2. The Hausdorff dimension, we get 2.71. Now that doesn't remind one of anything in particular, but if one then goes back in the literature and looks at what people found for DT in the old days, they also had quite bad data initially. So how does one extract the Hausdorff dimension? One looks at the volumes of concentric spheres and then plots the volumes against the radius and does finite size scaling. The problem here is in 2 dimensions, it's maybe just a 2-dimensional problem. The fluctuations are very large and there's no classical solution. So the quantum geometry is not a semi-classical object superposed by quantum fluctuations, but, well, there is no classical solution. So everything is just quantum fluctuation, and the fluctuations are very strong. Now, this is to be followed up, perhaps by an ambitious member of the audience who manages to solve this exactly, so I'm just putting this out as a challenge. So in 3D, the situation is quite clear, but it's very, very computationally extensive, so it's quite impossible to repeat what we did in 2+1, 3+1, but we believe now that, well, the time is probably dispensable. This is a proper time slicing. So that's a nice thing to say. Another aspect of universality of these models, perhaps quite generically so. I talked about phase diagrams. So here is a phase diagram of CDT, and it's the analog of what I showed you just a minute ago in terms of the DT phase diagram. We have here now one more constant, this anisotropy parameter delta, but otherwise things are very much the same. So what we have to do, this is lambda cosmological constant, we have to fine-tune lambda, as I said, you always have to do. So the really interesting phases we will be studying are on this codimension 1 surface. And here are just a few details about what the gravitational action looks like. So the weights I had to put when I wanted to evaluate my partition function. So they assume an extremely simple form because my basic building blocks are essentially all the same. Well, they come in 2 types, so you see them here in 4 dimensions. It has to do with the fact that we don't only have space-like edges, but also time-like edges. So that allows in a natural way to have 2 types of building blocks, and they appear in a specific way, a linear combination of the action. And this otherwise just is an action, very simple, depending on counting simplices of a certain dimension. So N2 is the number of 2 simplices, so triangles in a given configuration, and N4 is the number of 4 simplices in action. And so, yeah, it was never easier to evaluate the Einstein action than this type of framework. But that's of course known. So what we now do, we look at this has been known for some time, that this is a quantitative picture for the phase diagram is this. And we have now more recent results that examine on this 2-dimensional surface parameterized by this delta and kappa naught, the inverse Baer-Newton constant, the location and the order of the transition lines. So in particular, so the nice results about the de Sitter volume profiles, they just are located in phase C. Phase A and B, as you see kind of by these illustrative Monte Carlo snapshots of their volume profiles, they are qualitatively very different, and they do not seem to possess a nice 4-dimensional classical limit that would give some features of an extended 4-dimensional geometry. So from the point of view of quantum gravity, they're probably uninteresting. So we're sitting in this phase, and very interestingly, well, this is the first order phase transition line, we've located a second order phase transition line. So that's really the first time a second order phase transition like that has been seen in a system of random geometry in 4 dimensions, and still hasn't gone away under cross-examination by other parties. So this is very, very interesting that it's there. It's unprecedented, and of course one would like to look closer at what happens to the phase in the vicinity of the phase transition, because these points are natural candidates, of course, to define the continuum theory for quantum gravity. So we are very interested in understanding the scaling behavior in the vicinity of this phase transition line. So one way of doing this is in terms of trying to establish what are renormalization group flows. So what happens when you keep kind of physics fixed, and you, well, usually what you do is you send the Black's correlation to zero, to infinity. Yeah. We don't have a natural correlation function in this game, so we don't have nice two-point functions. But, well, so what we have done instead, we've looked at what happens when you take the linear lattice size, discrete lattice size, so the fourth root of the number of four-dimensional building blocks to infinity while keeping physics constant. Now, why is this non-trivial here? Well, we are in a theory where geometry is dynamical. And geometry being dynamical means also distance measurements being dynamical. Generally speaking, volume measurements being also dynamical. Yeah. So what do we mean? I mean, whereas the renormalization group, of course, crucially asks what happens when I change scale. So the difficulty is to define what one exactly means by scale in a theory where scale is dynamical. Okay. So you need some kind of physical yardsticks. And the only thing we have at our disposal at this moment comes really from this semi-classical fitting our ground state to a de Sitter shape that gives us two scales. One is the typical size of the de Sitter space, so it's dynamically determined, it emerges dynamically. Another one is the size of the typical quantum fluctuation. So we have two physical scales we can play around with. We don't have a correlation length, but we use those to define what we mean by keeping physics constant. And there's a preliminary investigation we've done using this idea and using also some simplifying assumptions on how scales and on how, well, I mentioned on the next page, how things happen as we move through coupling constant space. Some simplifying assumptions which you actually know not to be accurate. But it has allowed us to actually compute some renormalization flows, published in a recent paper. And here, well, what is this? This is a piece of the nice phase, the de Sitter phase C. So in particular, this was here the first order transition line. There was a corner here, if you remember, a triple point. And this is where the second order phase transition was. What you see here is a contour plot that involves two, not constants, I mean two parameters, they're called little omega and gamma, and we are extracting them. They're kind of universal quantities we extract through finite size scaling that characterize these volume profiles. Yeah. And the only thing you need to know to understand a little bit what happens in these plots is that when we take, as I said, we want to do the linear lattice size to infinity and 4, it translates to following flow lines where omega is constant. So this is a contour plot, so omega constant lines are exactly along the contours in the direction of growing gamma omega. So this plots gamma omega, and growing gamma omega means colors becoming lighter. So generally speaking, it means going this way in the phase diagram. Now, what we would have loved to see is to find flow lines that run into the second order transition line in some ways. Yeah? Then we can say, well, look, this is exactly what we're looking for. Here are the potential continuum theories, and this is the way the flow lines go. This doesn't really happen here. So the only thing, you could say, okay, if you flow maybe and go almost parallel to the second order transition, go into that region, well, clearly gamma omega grows, but it doesn't become infinity by any means. So is there a reason? So is this all bad? Well, it's not all bad because the simplifying assumptions we put in to get to these pictures are almost certainly wrong. So I mentioned them briefly here. So they were twofold. One was that the semi-classical interpretation in terms of mini-superspace is valid everywhere throughout phase C. So that means I can do this de Sitter fitting in a nice way. And secondly, lattice units in time and space direction correspond to the same physical proper times and proper distances also everywhere in the same way throughout phase space. And we already know neither of these is actually satisfied when we approach the second order critical line. So we cannot say anything definite yet. The only thing we have shown is given a proof of principle that even in a theory which is background independent and doesn't have any fixed scales to start with, you can make sense of these concepts. So, lastly, what this renormalization group study highlights is a need for more observables. Because you're saying you want to keep physics fixed, the more observables you have, the more alternatives you would have to specify what you actually mean by keeping physics fixed. And if you have many observables, there are many ways in which you can make the definition, and you can find RG flows and you can compare them and you check whether you find universal results. Now, here is one example of an observable we've looked at recently, and also it gives you kind of a proof of principle that many things can be done, and they turn out to be very easy and straightforward in this framework. So, what is special to observables in gravity, and what is captured in a very nice way by the framework of dynamical triangulations? Well, observables must be invariantly defined, without reference to coordinates. Coordinates are not geometry. Coordinates introduce gauge degrees of freedom, and without reference to a background metric. So that would be typically, of course, what we do in standard quantum field theory in Minkowski space. There is a given metric, and there is a given scale. These things will be determined, should come out dynamically out of the theory of quantum gravity. If you're lucky and clever, some standard QFT observables can be adapted to this context. So, and they can be made meaningful, so when you take a functional integral over all metrics, you get an object that has a non-trivial expectation value. It doesn't just average out to zero. So one example of adapting this is just some two-point function. You know, any, say, could be a scalar field, anything. Well, in the context of gravity, dynamic gravity, this wouldn't be a good observable G2 of 2 points x and y, because we cannot pin down what we mean by the point x here and the point y here. We could introduce a coordinate system, but that would make things coordinate dependent. However, what we can do using G2 of xy, we can construct an observable that is diffeomorphism invariant and doesn't depend on coordinates. And the way to do it is, that's is not due to me, but that has been worked out long ago, is to take this object G2 of x and y, integrate over all points x, y, but in order not to embrace all information, to fix that x and y should be a certain geodesic distance little r apart, and just put this into the delta function. Yeah? And this is all Euclidean, so the geodesic distance is just what it is. So this retains an information about all points of pairs separated by a distance r, and you can evaluate this in the sum of geometries. And you can then understand and explore what the behavior as a function of r is. And that has been done in simple with two-dimensional systems, and it works perfectly well. This is like a nice, has all the behaviors one would expect from a propagator. Now, if we applied a similar logic with other objects, well, one prominent thing you might look at is a gravitational Wilson loop. So everyone who's ever looked at Young Mills or other things knows what a Wilson loop is in non-linear gauge theory. So it's the trace of the path ordered exponential of the gauge potential. And in gravity, what we're putting here is the Levi-Civita connection. So that tells you how neighboring frames are related. So we can easily define this in continuum gravity, and what it does in field theory, of course, for small loops, it tells us something about F mu, yeah? So the field strength. What it does, also for small loops in classical gravity, it tells us something about curvature. And as a matter of fact, if you know all of the holomers that is this object without taking the trace locally, then you know everything there is to know about the curvature, so the remaining properties of a space. So the interest for us is capturing perhaps also curvature properties of quantum space. And that's something we haven't done, and also in other approaches in non-perturbative gravity, no one else has done. So the idea is, can we use an object like a gravitational Wilson loop to do that? Is that a candidate for a possible observable? And again, in a straightforward way, comparing with what I said about the two-point function, this alone cannot just be an observable, because here I referred to 2 points x and y. Here I'm now referring to an entire curve. And that's, of course, again, not a diffuse invariant concept. I have to say where the curve is and how the points of the curve relate to each other. So, but can we use it in a similar way, maybe to integrate suitably or look at other ways of characterizing the curves that is diffeomorphism invariant to compute Wilson loops and say something interesting about the underlying quantum space. So this is how far we've got. So our way of making these Wilson lines physical is to say, look, they're actually paths of a particle that moves around in space-time. So here is just a sketch of a piece of space-time. In CDT, we are now back to CDT. This is t equal to 0. This is t equal to finite time t. And what we usually do, we cyclically identify time. So this is a particle path that closes on itself, and well, it enables us in a nice way to point to a curve and to say, let us now just compute the Wilson line of the Lippi-Civita connection, the Wilson loop, along this loop. And that's what we've done. And that's something we've just measured in the simulation. So the topology we're using is S1 because S3. S1 refers to the compactified time, and S3 is just, as usual, the compact, the spatial slice. So what we do, we have a combined matter-gravity system where we add a single point, massive point particle to the path integral over all geometries. Yeah? And what is it? It's just a very almost trivial piece, just the mass of the particle times the length, the proper length of the path. So that's all you add to the action. And in the triangulation that becomes even simpler. This is just the bare mass M0, and NL just gives you the number of links that make up, or in this case, we are going actually on the dual, moving along the dual lattice. So it's the number of four simplices which the path passes through. So what we then do is we do our Monte Carlo simulations and we just measure the Wilson loops. And more specifically, what we do is we compute the holonomies, so they're valued, they're group valued, and then we extract two coordinate-independent trace invariants. There are two angles. Note that we are on SO4, frames are in 4 dimensions, and local frames are related, in this case, by SO4. All that can happen when you transport a vector around a closed loop is that it picks up an SO4 rotation. And these two angular variables we extract basically come from taking the trace of the line and the trace of the square of the line. So these are, of course, two group-valued matrices. And these are just two numbers. And what we can do is to understand how we look at the distribution of the theta 1 and the theta 2. So we average over many, many configurations, geometric configurations, over many, many of these Wilson lines. And what we measure is the distribution of these two angles. So these range from 0 to 2 pi. There's a trivial symmetry here. So actually, the measured data are only 1/4 of this quadrangle here. So these are the two angles, and this is the distribution. That's what we find. Now, interestingly, if the holonomies, so before taking the trace, if they were evenly distributed on the group manifold of SO4, then you can ask yourself, how would theta 1 and theta 2 be distributed. And that's something, it's a small calculation you can easily do. And it turns out that the distribution you get in this way matches perfectly the data we found here. So what we found is that the Wilson loops we are probing, they seem to trace out SO4 uniformly. I mean, in the sense of the Haar measure on SO4. So what we were after was a measure of curvature. But it would have only been a measure of curvature if, on average, our Wilson loops, at least in the naive way, would have come out as 1, so unit matrix in S4, SO4, plus some terms, curvature that define a curvature. This is not how it comes out, at least not for the class of loops we have looked at, but we find only kind of the zeroth order contribution, and however that fills out SO4 uniformly. So that's, again, interesting for a couple of reasons. Namely, one could have been worried that SO4 would only be very selectively sampled because, the angles that contribute to the holonomies, they jump in discrete bits because we have only discrete building blocks, and there's only a couple of angles which are rather large that contribute just to jumping around in SO4. So what we found is there is no obvious trace of this discretization effect, but we get a very smooth sampling of the SO4. And another thing is, of course, we are working in a completely coordinate-free approach, and this requires an intermediate stage to introduce some coordinates, but we've shown it's very easily possible. But all dependence on these coordinates, of course, drops out in the end as soon as we start taking traces and computing this invariance. So computing holonomies and Wilson loops in gravity has never been easier than in this particular setting, I would claim. Okay, that finishes my story of the day. I've looked with you at a cross-section of properties of CDT quantum gravity. I said that's a candidate theory of quantum gravity, which you should take seriously. We have investigated various properties with highly non-trivial results. So emergence of macroscopic four-dimensional geometry, that was this classical result I mentioned, where the crucial input, like perhaps also with the other result, is the presence of the causal structure, using different building blocks. There's an interesting variant of CDTs, these locally causal dynamical triangulations, which I've introduced you briefly to make the point that apparently the crucial thing is not the time slicing, but the crucial thing seems to be the local lighting conditions. Something I haven't talked about today, but can also almost count as a classic and has stimulated many people to repeat the calculation. That is, one can compute or rather measure the spectral dimension of these quantum geometries that appear here in CDT, and there seems to be coming from dimension 4 for macroscopic probes. When you get close to the Planck scale, it seems to approach a value that is closer to 2 there. So that's what we call dynamical dimensional reduction. That's a very non-trivial phenomenon that many other people have investigated in other approaches and find often similar things. I showed you the phase diagram, and very interestingly, it has a line of second-order phase transitions, which are natural candidates for taking non-trivial scaling movements, continuum movements. And I've also mentioned briefly that we have already implemented renormalization group flows, and it's remarkable that one can actually do that in a background-independent and non-perturbed setting like this one. As observables, well, you've seen we can measure Wilson loops, but we need to improve on what we do with the Wilson loops to get any interesting observables out, for instance, that might tell us about coarse-grained curvature. But in general, we need, as in every approach to quantum gravity, observables. Now, I hope I've convinced you that CDT quantum gravity is an exciting story, and it definitely keeps going. Thank you so much.
Thanks very much, Renate. Questions?
This calculation of the distribution of angles of the Wilson loop, that was carried out in which region of the phase space?
In C. In the interior of C, so where we see nice semi-classic behavior, yeah. Yes,
but
good
shouldn't
point.
you so explore other regions, the approach of the critical line, or?
Yes, but this was, but it was a preliminary, I mean, for, usually when we say now observables, also we calculate, say, Hausdorff dimension, it has always been at points well in the interior of that phase. Of course, especially if you're interested in what happens on small scales, and as you go to the large scale, you should approach this line precisely. Yes.
Also, in the beginning, you said that your construction is falsifiable. What do you have in mind?
Well, for instance, measuring, that's in a way how people falsified, of course, there are always loopholes, we know that in this complex type of theories, how they falsified the precursors, the Euclidean dynamical triangulations. So, for instance, by this bulk measurement of Hausdorff and spectral dimensions. So if you insist that in some kind of limit you want to get a four-dimensional object coming out, and the Hausdorff dimension never becomes 4, well, then you falsified the model. So in that sense, so it's a non-trivial handle you have here. It's not that you cannot say anything. Of course, any measurement has error bars, and you have to ask yourself, about all kinds of systematic errors, etc., that might appear. But in principle, you have a quantitative way of testing hypotheses and also testing the correctness. In this case, correctness of a certain classical limit.
And you write down a matrix model for the two-dimensional LCDTs.
Yeah, one can do it. One can generalize a method, a way of writing it that Dario and Johansson.
But you can't solve it.
They could already, they couldn't solve the CD, I'm not saying that the CDT version, matrix model version, wasn't solved. It's basically just putting in a way that, constraining the local, what happens around a vertex. So I think if I could get it to work for the CDT, since this is just a slight generalization of what is allowed at vertices, one might also be able to do it with LCDT, but it hasn't been done.
Any further questions? Sorry.
You have a line of second order points.
Yes.
Have you identified any operator which moves you along this line? Which would, like for instance, the equivalent of the 2DXY model in which you have the vorticity, the number of vortices drives you along this line. Is there anything you can identify there?
It brings me back to the question of observables. So what are nice observables that in the vicinity would allow me to distinguish between one and the other? We don't really know those yet. There is a conjecture that some of these points may have a space-time anisotropy in them. So there could be Hojava-Lifshitz-like. But for that, I would need to have an observable that pins it down, in a coordinate, in a well-defined way. And we don't really have those to discriminate the situation. Yeah.
Okay, let's slide the speaker again.